On September the 23rd, 1999, tensions were high at NASA. The agency's engineers were watching with anticipation as their latest mission, a satellite named the Mars Climate Orbiter, approached its final destination, the Red Planet. The orbiter, you can see behind me, was a huge project that had taken years of development. It cost $125 million and had traveled through space for 10 months over a distance of 200 million kilometers. Once it arrived at Mars, the probe's job was to sit in orbit and study the climate. At around 9 a.m. on the morning of the 23rd, the orbiter made its final approach, thrusters firing to ease it into position above the surface of the planet. The engineers knew as the satellite began to pass around to the far side of Mars that they would lose communication. But in 20 minutes' time, the probe would re-establish contact and begin its mission. That contact never came. The Mars orbiter never phoned home. In the days that followed, NASA frantically investigated what could have possibly gone wrong. They scoured the mission data and eventually discovered the error. While NASA's own engineers had been working in metric, using kilograms and meters to design the satellite, contractors at Lockheed Martin had been working in imperial, using pounds and feet. NASA announced that this miscommunication in measurement had doomed the orbiter. Fed the wrong units, the satellite's thrusters had misfired, and it had either bounced off the Martian atmosphere into space, lost forever, or burned up on contact. All that money, all that effort, gone in an instant because someone had forgotten to convert imperial to metric. As John Logsdon, a professor of space policy and a former NASA staff member, told journalists at the time, "That is so dumb." Now, I like this story as a way to talk about measurement because it illustrates a number of things. First, it shows that measurement is a communication tool. It's a form of language, a way of sharing knowledge and helping people work together. Second, it shows that measurement is cultural. Different units are used in different countries for different purposes, and the history of metrology, the science of measurement, is one of searching for the right measures at the right time. And third, the story shows that measurement is one of the most powerful tools our species has at its disposal. Get the measurements right and you can travel to other planets. Get them wrong and you'll blow up when you get there. In this talk, I'm going to try and explain a little bit about why and how measurement attained this prominent but overlooked position in all our lives. Measurement, I think, is as important to humanity as mathematics or the written word, but because of its reputation, because we associate measurement with pedants and bores, with people who know, as they say, the measure of everything and the value of nothing, we ignore it. But to ignore measurement is to ignore one of the primary driving forces of science, of society, and of progress. So, we're going to start a little by talking about the ancient origins of measurement. The historian Robert P. Crease says units of measurement have three qualities if they are to be successful. They must be accessible, they must be appropriate, and they must be consistent. Accessible because for most of its history, measurement has been something done with the eyes and the hands. So you want to have units that are graspable and familiar. Appropriate because while you can measure mountains with matchsticks, it takes too long. The unit must fit the subject. And consistent because measurement strives to create facts, to create information that is shared and that is reliable. That means measures should not change. So where do we find these attributes in the world around us? Well, let's go back to around 4000 BC, where we have the first evidence of systematic measurement and, not coincidentally, the first evidence of humans settling together in the first cities, in places like the Indus Valley, in Mesopotamia in the Middle East, and in ancient China and Egypt. Now, in these places, to create the first units of measurement, humans turned to their own bodies. As the ancient Greek philosopher Pythagoras put it, man is the measure of all things. And this applies in both a metaphorical and in a very literal sense. Just about every ancient measurement system derives units from the human body, with the first units generally being the foot, the hand, the pace, and the outstretched arms. Now you can see an example of this in the picture behind me. This is a carving known as the metrological relief, which is from ancient Greece around 430 BC. In it, you can see some of the basic Greek units of measurement and the body parts they correspond to. You can see an imprint of a foot just above the shoulder there. You can see the hand itself, and of course you can see the orologi, the fathom, the outstretched arms. Now, these are familiar units, but some cultures have turned the body into a fascinatingly rich index of measurement. The Maori people of New Zealand, for example, have created more than a dozen units derived from the body, ranging in size from the smallest joint of the thumb to the distance from your toes to your outstretched arms above your head. The legacy of this sort of measurement is still with us today with imperial units, that is, feet, yard, and inches, as used in the US and often in the UK. So this is a little demonstration, and apologies for this. But so, you have the basic unit of the inch, which is usually taken to be the flat across the middle of the thumb. You have 3 inches, that makes a palm. You add another inch, you have the hand. You have 9 inches, which is usually from the tip of the thumb to the little finger, that is a span. 2 more inches makes a foot. Then you take from the middle of the sternum out to the side like this. This is 3 feet, this is a yard. And then you double it all the way, and you get a fathom, which is 6 feet, which is my height as well. That's the hardest part of the demonstration there. Now, this only works for me because I happen to be 6 feet tall. If you're the average height of a woman in Italy, for example, which is around 5'4", then all those measurements are 12% smaller. Now, this may sound like an obvious observation to make, that units of measurement derived from the body differ based on the body being used, but it's worth bringing up because it shows 2 things. First of all, that for all the importance we give units of measurement, they are essentially arbitrary. We make them up and we define them. And second, measurement itself is subject to bias. Despite the appearance of objectivity that measurement affords, it often changes based on who is doing the measuring. So these bodily units are the first ancient measures. Oh, that's too quick, sorry. But when you use them, you quickly run into problems. First, these measurements don't apply so well to large scales. So for measuring long distances, ancient cultures had to come up with much more inventive units. These included things like the bow shot, the axe throw, the stone's throw, but stranger ones as well. So in the Nicobar Islands in the Indian Ocean, for example, journeys were measured in the number of coconuts you would need to sustain yourself going over. So if you're traveling to the island next door, you might say, oh, that's a 3 coconut journey. If you're going a bit further away, you might say, that's a 10 coconut. God, we've already got to stock up for that one. Now, the Sami people of northern Europe had a unit known as the poronkusema, or the distance a reindeer walks before stopping to urinate. If you're curious, that is about 7.5 kilometers. It sounds like a weird way to measure distance, but if you spend your life herding reindeer around, then it'll come up pretty organically. These units show the second problem with early forms of measurement, and that is a lack of standardization. Say you're measuring distance using bow shots, for example. Well, like my demonstration with the tape measure, the important question becomes, who is the one doing the firing of the bow? Do they fire at the same distance every time? And how do you measure that without a consistent unit to use as a reference point? This is a problem, and we have evidence of people both trying to adapt to this and take advantage of it also. In Ethiopia, for example, there was a practice for each village having a designated measurement man who'd come with you on market days when you went to buy goods. And what made this man useful? Well, he was the man with the longest arms in the village. So when he went to measure lengths of cloth or timber, you knew you were getting a good deal. This sort of problem meant that standardization, consistency in measurement, became a very important civic function. As societies advanced and became more complex, they wanted to do things like map out territories, like build cities, conduct trade, collect taxes, all of these activities which benefited hugely from standardizing units of measurement. This meant that the people in charge of society, the rulers and the kings, would often create physical standards to represent units, sharing official copies among citizens in various ways. In ancient Egypt, for example, the cubit was the standard unit of measurement for length, and it's the distance from your elbow to the fingertip. It comes from the Latin cubitum, meaning elbow. It was used to build everything from irrigation channels to the pyramids themselves. And to ensure its consistency, builders would have to compare their cubit standards with those of their overseers on a regular basis. If they failed to make these check-ins, they'd be punished. This is how measurement became a tool for coordinating society. It helps us work together. Now, these sorts of public standards for units were common for a long time, and I have to mention this one quickly, which I went to earlier by accident, because of where we are. So here is a picture of some amazing measurement standards from Padua itself. These were carved into the corner of the Palazzo della Ragioni in 1277, and they show 4 different standards from left to right for grain, for bread, I believe, and for bricks and for cloth. And yes, I brought my panino along to compare. It was a perfect size. I was fine. Just to drive home, though, this link between civilization and measurement, I want to show you one last example. Now, this is the Louvre stele, which records the Code of Hammurabi, one of the world's oldest legal texts. That dates to around 1750 BC in ancient Babylon. Now, not only does the text itself contain a number of rules about measurement, laws about punishing traders who don't serve you a full flagon of wine, for example, but the iconography on the stele itself illustrates the deep-rooted association between measurement, power, and society. So if we look a bit closer on the top of the stele here, you have 2 figures. So the standing figure on the left is King Hammurabi himself, and the sitting one is the Babylonian god of justice, known as Shamash. Now Shamash, as you can see, is handing 2 items over to Hammurabi, a rod and a coil of rope. Now, we don't know for certain what these are, but archaeologists believe they are measuring tools. What Shamash is handing over is essentially a ruler and a tape measure. It shows that these are the tools of civilization, so important that they have to be handed down by the gods themselves. So that was the origins of measurement, and now we're going to look at what I like to call the quantified revolution. So measurement has deep roots as a way of organizing society. But it took a long time before we realized its utility as an epistemological tool, as a way of creating and verifying knowledge. This change was momentous, and it took place over the course of many centuries, from the 1400s onwards, in a period we now call the Scientific Revolution. It's important to understand that prior to this era, measurement, observation, experiments, these were not seen as particularly trustworthy exploits. The intellectual climate was dominated by the ancient Greeks, and particularly by philosophers like Plato and Aristotle, who prioritized metaphysical knowledge over the empirical. Think of, for example, Plato's theory of the forms, which says that the physical world is only a shadow of the immaterial realm of unchanging ideas, and it's those immaterial ideas which contain true knowledge. That puts physical evidence lower down this hierarchy of truth. Plato had a little demonstration for this. He said, hold up your hand in front of your face and examine your fingers, particularly the littlest, the ring finger, and the middle finger. Your senses tell you that your ring finger in the middle there is larger than your little finger, but it's smaller than your middle finger. How can something be both smaller and larger at the same time? Now, it seems like a silly demonstration, but Plato's conclusion was that perception was not necessarily to be trusted. And this was true of anything you might think to measure, not just your hands in front of your face. Measuring things was fine for builders, said Plato, but you can't measure truth. You can't measure knowledge. From the early Middle Ages on, though, this approach was challenged in numerous quarters. One particularly important influence was what historians sometimes call artist engineers. This was a class of practical artisans who built stuff with their hands, everything from cathedrals to great sculptures and paintings to weapons and engineering tools and so on. All of these disciplines required accuracy and the ability to measure. The success of these tools seeped into the culture, and in Europe from the 14th century onwards, there's a sort of passion for quantification that springs up in many different disciplines. In music, you get the invention of the musical staff, which divides melodies into precise tones and rhythms. In painting, you have the introduction of perspective, where painters used grids to view the world and divide up images. We have, I think, an example here from Albrecht Dürer, which is a woodcut of a painter getting a close look at a woman, shall we say, using a grid to help. And you have the invention of a number of scientific instruments that allowed for accurate measurement of the world. First, there's the clock to measure time, of course, and then from the 1600s onwards, you have the telescope, the microscope, the barometer, the thermometer, and so on. Now, it's hard to quickly or adequately describe all the scientific achievements we owe to these tools and their measuring capability, but one of the most momentous examples is the Copernican revolution, the replacement of the old Aristotelian cosmos, in which the Earth is the center of the universe, surrounded by concentric crystalline spheres, with the solar system that we know today, with the sun at the center and the planets orbiting in elliptical paths. So the process by which this evolution took place had many causes. I'm sorry, I've got my slides mixed up, but measurement was a key factor. It was the meticulous celestial measures of the Danish astronomer Tycho Brahe who provided the raw data from which Johannes Kepler derived his laws of planetary motion. And it was the observations of Galileo Galilei, who taught at this very university, of course, that convinced many of the truth of this new cosmos. With his telescope, Galileo observed spots on the face of the sun, the phases of Venus, the moons of Jupiter, and the mountains and valleys on the moon. And not only did Galileo observe these phenomena, but he measured them too. It was quite one thing for him to say, with my telescope, I have seen the mountains on the moon. It was another thing to say, and they're 4 miles high. What an astounding thing that was, to claim that knowledge for the first time, to project the reach of the human senses and human reason beyond the terrestrial sphere. This is the power of measurement, to make the world around us and the world far away from us real and known. As the British scientist Lord Kelvin would later put this in the 19th century, when you can measure what you are speaking about and express it in numbers, you know something about it. When you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science. So, one historical event that shows this change in the importance of measurement and its new link with science is the creation of the metric system during the French Revolution, as illustrated here. Now, this is a complicated story and one of my favorite episodes in the history of metrology, but to keep it short, measurement in France before the revolution was an absolute mess. There was no central authority standardizing units across the country. One estimate suggests there were more than 1,000 different units in use in France, each of which had hundreds of variations. When journeying through the country in 1789, the English travel writer Arthur Young bemoaned what he called the tormenting variations of the country's units. He wrote, "The infinite perplexity of measures exceeds all comprehension. They differ not only in every province, but in every district and almost in every town." So, for example, the common capacity unit of the pint ranged in size from 0.9 litres in Paris to 3.3 litres in Plessis-Soutil. The most common measure of cloth, the aune, could refer to one of 17 national variations, ranging in size from roughly 300 to 600 lis. And how long was a lis? Well, about 2 millimeters, but again, it depended. This was such a problem, it was so annoying and so confusing, that when the French were collecting the grievances of the people in the run-up to the revolution in the cahiers de doléances, the notebooks of complaint, problems with measurement were the 14th most frequently mentioned item out of 50. They were brought up more often than complaints about the courts or about the infringement of personal liberty. Fixing France's measures then became both a political and a scientific problem. The revolutionaries had a slogan. What they wanted was one law, one weight, one measure. They wanted to make the lives of the common folk easier and standardizing units of measurement in line with the ideals of the Enlightenment. But they didn't just want to be egalitarian, they wanted to be rational too, to prove France's place as the scientific leader in this age. So to fix this problem, they gathered some of the greatest scientists of the time, thinkers like Pierre-Simon Laplace and Antoine Lavoisier, to forge a new set of measures. These are seen here, these are in a mess. There we go, seen here, the new measures. They wanted to create a system not just for France, but for the world, that would symbolize the potential of this newly empowered republican nation, and that would be à tout le temps, à tout le peuple, for all times and for all people. To do this, they gave the metric system, as it would become to be known, 3 important attributes. First, there would be new names for each unit, new prefixes and suffixes taken from the ancient Greek and Latin to define the different magnitudes. These included familiar terms like kilo for 1,000 and cent for 100th, and also less common terms like deci for a tenth, demi for a half, and prefixes that are now completely forgotten, like myria for 10,000. Second, the units would be interconnected. They would support one another. So the unit of length, the meter, would be divided by 10 to create a decimeter. Then, by creating a cube with the sides each a decimeter in length, you would have the standard unit of capacity, the liter. Then you would fill that cube with water and weigh it, and you would have the standard unit of weight, the kilogram. These bonds would mutually reinforce each of the unit's values, thought the scientists. No single unit could fall into imprecision when it was held in place by its brethren. Perhaps the biggest change, though, was that the metric system would be decimal, denoted in base 10. This clearly shows the influence of scientists, as decimal was not at all widespread outside of scientific discourse. Most measuring systems, as with the imperial system, were denoted in base 12 or base 16, so 12 inches in a foot, 16 ounces in a pound. Now, these divisions are handy if you're doing quick calculations at the market, as you can easily quarter, third, or halved units without worrying about weird fractions or decimal places. But base 10 works much better on paper, because you can quickly change magnitudes simply by moving the decimal point about. As a consequence, it's much better at dealing with both very large and with very small figures, which benefited the scientists. To fix this system in place, though, the French needed a keystone measure, the meter, the unit from which all others would be derived. A number of proposals were made for how to define this unit, but eventually it was decided that a meter would be equal to 1/10,000,000th of the distance from the North Pole to the equator, a division of the meridian line seen here. They were measuring the meridian through Paris, though. I think this one goes through London, but about the same. The meter would replace the most common unit of length in ancien régime France, the pied du roi, literally the foot of the king. This unit, as the name suggested, was supposedly based on the size of the monarch's feet, dating all the way back to Charlemagne. And this switch from pied du roi to meter encapsulates the ambition of the era and the changing fortunes of measurement. Like the French Revolution itself, this change was a transition in power. People went from trusting the old feudal system, defining units using the body, to trusting in science and to mankind's common inheritance, the earth itself. Now, in 1799, the meter was finalized. It was turned into a physical metal bar, which you can see here. I was lucky enough to see this in the French National Archives a few years ago. And physical copies of this bar were distributed around the country. The scientist Laplace boasted that now, with the new meter, every farmer in France could say, "The field that nourishes my children is a known portion of the globe, and so, in proportion, am I a co-owner of the world." Or, as Napoleon put it, a little bit more succinctly, "Conquests will come and go, but this work will endure." So, last section for now, measurement today. Now, Napoleon was right. The French Empire is no more, but the meter is still with us. In fact, it conquered the world far more effectively than Napoleon's armies ever did, and is now a central part of what we call the Système International, the SI, or the metric system, with its 7 based units seen around the edges here. These are used by every nation on the planet to one degree or another. Enlightenment thinkers used to dream about uniting the world with a global currency or a global language. That never happened, but we do have global units. We have one law, one weight, one measure. But while the units themselves are the same, the way we define them has changed significantly since the French Revolution. It turns out that even the Earth itself isn't a guarantor of precision. The scientists who made the meter underestimated how irregular the surface of our planet is. It's an oblate spheroid with a buckled and crumpled surface, and the length of the meridian therefore differs depending on where it's being measured. In fact, the meter itself is, in some senses, wrong. It never was and never has been exactly 1/10,000,000th of the distance from the North Pole to the equator. Mistakes were made when its length was being calculated in the 18th century, and modern satellite surveys of the planet have revealed that the meter was, and remains today, 0.2 millimeters short of the original target value. And it's not very much. That's about the thickness of a few sheets of paper. A shortfall, though, that's been enshrined in every meter made ever since. This sort of inaccuracy was less noticeable during the 18th century, but as our tools and techniques have advanced, scientists have demanded increasingly precise measurements. The best example of this problem, and it's the problem that first got me interested in the subject of measurement altogether, is this object here. Inside those bell jars, if you can just make it out right in the middle, that little small shiny thing, that small lump of metal, that is the international prototype kilogram, otherwise known as the IPK, or le Grand K. And since the French Revolution, it has been a lump of metal like this that was the definition of a kilogram. Whatever that lump of metal weighed, the kilogram weighed, no more and no less. I first heard about the IPK back in 2018 when I was sent on a reporting trip to BIPM, the Bureau International de Poids de Mesure, which is the international agency tasked with maintaining the standards of the metric system. The IPK is kept in the headquarters of BIPM in an underground vault near Paris. 3 keys are required to open the vault, and each key is kept by an emissary from a different country. Now, the original kilogram standard was created during the French Revolution, derived from the meter, and replaced by this one, the IPK, in 1879. This standard is made from a platinum iridium alloy, an incredibly stable and incredibly dense, very heavy metal. Here's another picture. This is of the US copy of the IPK. There were many copies made at the same time. It's hard to get a sense of scale from these pictures, but the kilogram is only about 1.5 inches tall. It's so dense that one of the keepers at the BIPM told me that the first time he went to pick it up, he almost dropped it, because humans are simply not used to holding something so small that's so heavy. Now, you'll notice I've been talking about the IPK in the past tense. And that's because the reason I'd gone to the BIPM was that there was a problem with the kilogram. 3 times since it was created, the BIPM had opened up the kilogram's vault to check its weight, to see that a kilogram still weighed a kilogram, by comparing it with a number of copies made at the same time, known as the témoin, or witness kilograms, like this one here. But from the 1970s on, the scientists noticed, much to their dismay, that the prototype kilogram was losing weight. Not by much, just 50 micrograms, which is about the same weight as a single eyelash or the residue left behind by a fingerprint. But in today's high-precision world, this loss of accuracy was troubling. What was stranger is that the IPK technically couldn't lose weight, as it was the definition of the kilogram. Theoretically, the IPK was not getting lighter. The rest of the universe was getting slightly heavier. The solution to this problem was both incredibly simple and devastatingly complex. The scientists needed to redefine the kilogram, to get rid of the physical standards altogether, and instead derive its value, that same amount of mass, from some new and more stable source. Luckily, this was a problem that metrologists had encountered before. The kilogram wasn't the first standard to reveal this sort of variation, and since the 1960s, scientists have actually been replacing every physical standard used in the metric system with calculations based on the fundamental constants of nature, defining units of measurement using properties that we believe to be inherent and unchanging throughout reality. The meter, for example, is no longer equal to the length of a metal bar or 1/10,000,000th of the Earth's quarter meridian, but to the distance traveled by light in, and this is going to be tricky, and I hope the translation is good, traveled by light in 1,299,792,458ths of a second. The second in term is no longer defined as a solar day divided by 86,400, but the duration of, another long number, 9,192,631,770 cycles of cesium-133. radioactive atom. Those cycles are, they're sort of like an atom's internal pendulum as it flips between different energy states. So the IPK was the last remaining physical standard, and it's now defined, instead of using a lump of metal, using this thing here, which is known as a Kibble balance, or previously a Watt balance. Now, the physics behind this are a little bit complicated to explain fully in such a short talk, but essentially the Kibble balance defines it weighs things using electromagnetic forces, which are themselves measured using quantum constants. These constants include Planck's constant, which describes the relationship between the frequency of a photon, the particle of light, and its energy. But you can also think of Planck's constant as the smallest physical action that we can observe in the macro world before reality breaks down into quantum uncertainty. So in 2018, I went to Versailles, the headquarters of BIPM, and watched scientists as they voted in to use the Kibble balance for the new definition of the kilogram. The ones I spoke to seemed happy, dazed, a little bit relieved, but they told me that by redefining the kilogram, by getting rid of the last physical artifact used to define the metric system, they were fulfilling the dream of its creators during the French Revolution. They were anchoring units of measurement in the very building blocks of reality, in the speed of light and in the spin of atoms. And by doing so, they said they had finally made the science of measurement à tout le temps, à tout le peuple, for all times and for all people. Now, I started this talk with an example of scientific measurement gone wrong. So I want to finish it with an example of measurement going very right. And since I've been talking a lot about length, about cubits and meters and so on, I want to talk now a little about the most precise ruler ever built, otherwise known as LIGO, or the Laser Interferometer Gravitational Observatory. Now, you might remember LIGO from news stories in 2016. It's a huge scientific project that you can see right here, built for the purpose of detecting gravitational waves. These gravitational waves are minute ripples in space-time caused by massive cosmic events like the explosion of stars. They were first predicted by Einstein in 1916 as a proof of the general theory of relativity, but they were only observed for the first time by LIGO in 2015, with the results announced in 2016. So LIGO, the observatory, consists of a pair of laser beams angled perpendicular to one another in an L shape. There's these two L's coming off that central block in the middle there. Each of those arms is 4 kilometers long, and when LIGO is hit by a gravitational wave, the laser beams within them shift very slightly out of step with one another. This sounds like a simple process, but the level of precision needed to detect these wobbles is astounding. LIGO is so sensitive that it's able to register changes in distance just 1/10,000th the width of a proton. And a proton itself is already 100,000 times smaller than an atom. This level of precision is the same as measuring the distance from the Earth to our nearest star, 4.2 light years away, and getting that accurate to the width of a single human hair. We've come a long way since measuring things with bow shots. Now, when LIGO successfully detected gravitational waves for the first time, it was the smallest, the most accurate measurement that humanity has ever made. Yet, what it was measuring was this: the collision of two black holes, each 30 times more massive than our sun. And this collision was taking place a billion light years away in another part of the universe. Scientists hope that future experiments similar to LIGO, but operating in space, will be able to detect gravitational waves from even more distant events than this, including perhaps the formation of the universe itself, ripples from the start of creation, from the Big Bang. Now this, for me, sums up the awesome power of measurement. The discipline started thousands of years ago with crude and basic units that we defined using our own bodies. With these tools, we were able to make sense of the world around us. And since then, we have measured not only the Earth and the stars, but also our place in the cosmos. Measurement is pushing the frontiers of knowledge even further still. With experiments like LIGO, we now measure phenomena that previously we would have thought impossibly small and incomprehensibly large. We make both of these extremes tangible to humans. humans who try, who fail, and who sometimes succeed to be the measure of all things. Thank you very much.